numbering formats and counting systems. So why don't we get started and talk about it and study base 10 that we're so used to. So base 10, we have 10 different symbols, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And there's no symbol for the number 10. Because here are the 10 symbols starting from 0, 1 through 10. So once we get above 9, we roll over. So yeah. Anyhow, so we end up with when you do a larger number, you have the first column, which is the ones digit, which are single ones. That's actually 10 to the 0 power, which equals 1. 1 times 10 to the 0. The next column is going to be 10 times that, because you have to add up 10 of these symbols before it overflows to the next digit. So this digit is the 10 to the 1 power, which is 10. And the next overflow digit would be the hundreds column. So this is going to be 10 squared. And then the next digit is going to be the thousands. So 10 to the third. So you kind of see the pattern here, 0, 1, 2, 3, etc. And we've gotten so used to this and works quite well. So what we're in computers, we use binary a lot because computers just knows ones and zeros. So in binary, it's base 2. This is base 10. Binary is base 2, which means we only have 2 symbols. It's on or off. We got 0 or 1. That's it. If you have more than 2, it overflows to the next digit. So therefore, the first digit, just like this, is still the ones, or 2 to the 0 power. The next digit, which it's going to be the 2s, see, this is the 10s, these are going to be the 2s, so it's 2 to the 1 power. So if there's a 1 in here, that means there's 1, 2 in the value of the number. The next column is going to be 2 squared, which is, actually I should write this. This is the 1s, this are the 2s, these are going to be the 4s. Just like here, these are the 1s, these are the 10s, these are the 100s, these are the 1000s. So that's the 2s column. We add one more digit, 2 cubed, which is 8. Sorry, sticking in my head here. Next column is 2 to the 4th, which would be 16s. Next column, 2 to the 5th, it's going to be 32s. And you see it just like this goes by 10, 1, 10, 100, 1,000, 10,000, etc. This is going to go by factors of 2. 1, 2, 4, 8, 16, 32. It'll double every column, it doubles. So it's pretty straightforward here. So let's count in binary. Yeah, 1, 2, 3, 4, 5. We'll start with 0, all zeros. So 1, obviously everything stays 0. We add one more to this. It's going to be 0, then the 1, because this I'll add in this column here what it is in base 10. 0, 1, 2. Obviously zeros. We add one more, be 1, 1, 0, 0, 0. So this is a 3. Now, if we add one more, that's going to overflow, and this is going to overflow. So it'll be 0, 0, 1, 0, 0. This is going to equal 4. And likewise, 0, 1, 0, 0. That's a 5. 0, 1, 1, 0, 0 is a 6. 0, 0, 1, 1, 1 is a 7. 0, 0, whoops. 0, 1, 0, 0, 0 is an 8. Because these are the eights column. Remember, this is the ones column. These are the twos column. These are the fours column. These are the eights column, and these are the 16s column. And you see we have a 1 in the eights column, so we have the number 8. And I'm not going to be tall enough to continue here, but you see the pattern of how to count in binary. What it's going to be handy here is, aside from numbering, is knowing how to translate. We use translating to decimal. It's not all that hard. You learn some of these. You can do the powers of 10. So like this one, I can say, okay, I have one of the fours column. So I have 1 4 plus another 1. That means 5. So I have a 5. Um, and you notice, I want you to notice something. And that is, when I got to 8, 7, and then 8, it overflowed. So 3 digits will have 8 different values. If I were to continue, you'd find out that 4 digits has 16 different values. So we can translate very easily between things that are powers of 2. So numbers that are powers of 2. If we were to translate binary to octal, octal is base 8. I'm old enough to remember I first learned to program mainframe computers that use mostly octal. So the easiest thing was to convert to binary and then convert to octal by taking every 3 digits, looking at the number and converting it to octal. For hexadecimal, which I'll explain more in a second, we use 4 because hexadecimal means 16, and that's 16 different values. So let's we don't really use octal hardly at all. It's very, very rare anymore. You'll see octal latches and stuff like that, and that's just because there's only 3 bits for addressing. For the most part, we're going to use hex a lot. So learning hex is going to be very important. Let me redraw this to show all the hex numbers. The binary representation counting from 0 to 15. And so therefore, we count 0, there are 16 different symbols, and we're using 4 different bits. This is hexadecimal. So hexadecimal, you use 4 bits of binary, and you can represent 16 different numbers. So that's 2 to the 4. 2 times 2 is 4, 2 times 4 is 8, 2 times 8 is 16. So we have 16 different values we can represent with 4 bits of binary. To represent this, we can't use decimals. I use decimals here because we're very familiar with it. If we're going to use single symbols in hexadecimal, we have to have single symbols. We can't go to 2 digits. So the actual hexadecimal symbols are going to be, we need 16 different symbols. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We can't use 1 0, so we go to letters. So A is a 10, then B, C, D, E, F. So if you want to start to remember some of these, there are some easy ones. Look, obviously 0 and 1 is quite easy. Let's say more. 15 is quite easy. F is all ones. That one's pretty easy. there's another one that I find super easy, and that's the number 10. Because the number 10 is 1010 or A. A, after a while you work with this enough, you get to know A is a 10. So 1010 is the letter A. So if you want to go to B, just add 1 to it. 10 11, 10 with 1 more. And likewise, 9 is an easy pattern because it's a 1 0 0 1. You have ones on each side. And 7 is easy because it's 3 digits of 1. Just like 15 is all ones before we go over to the next digit. These are all ones before we have to overflow to the next digit. And obviously the next digit is an 8, so that's an easy one to remember. Um, the other thing about binary, um, in decimal, if we have 1,000, 1,500. If I want to divide that by 10, by the base, divide that by 10, I just move this over 1 digit and say 150. I divided it by 10. If I want to multiply by 10, I just add a digit, 5000. I slide it this way. If I want to multiply it by 10. So in binary, it's the same thing, except the base is 2. So if I want to take the number 10, if I want to divide that in half, the number 5, I'm just going to slide these digits over to the right by 1 column, which would be 101. Well, wouldn't you know it? 101 is a 5. So if you memorize 10, you know 5 already. Boom, you're done because you just divide it down. Likewise, if you'll know 4, 4 is fairly easy because it's just a 1 in the fours column. Multiply that by 2, you get 8. You get the 8 here, 1 and then 3 zeros. So you'll find this a lot. 2 is easy because it's just a 1 in the twos column. 3 is just 2 ones. So you start filling in the blanks after a while. Multiply 3 by 2, you get 6. So if I slide this over, I'll have 110, which is 6. Likewise, 6, you can divide it down, you can get a 3. So it kind of helps. I can think backwards. Between 15, I can subtract 1 by making that 0, so I know that's an E. So going from F to E, it's just make the ones column a 0. You start to learn them. C is one I've learned because it's 1100. It's an interesting pattern. So that's my suggestion is you learn pieces of this, and the more you work with it, the better. The reason why hexadecimal is so important in working with DSPs and stuff is because we go by bytes. 1 byte is 8 bits. Each one of these digits in binary is a bit, and so 1 byte is 8 bits. So we'll have 1, 2, 3, 4, 5, 6, 7, 8 bits. Well, these 8 bits will divide nicely in groups of 4. So you can represent this as a hexadecimal number quite easily, which obviously in this case is 0, 0. But if I were to make this a little more random, you know, so what did I say 1010 was? That one, hold on. 1010 is the number 10, right? Which is an A. 1010 is an A. This is 110, that's a 6, because it's 3 multiplied by 2, so that's a 6. So this number in binary is a 6A in hexadecimal. This column obviously is the 16ths. So that's the tricks I've used to learn really quickly. You have to be pretty fluent in going back and forth because a lot of times you're sending data, if you're using bits to mean certain things in registers, it's very important in a register because certain bits will turn on certain things. And so you have to be very quick at grabbing a, a hexadecimal number and knowing where the ones and where the zeros are. Um, then you know what you're turning on or off in a particular register. So 1 byte is going to be 2 hexadecimal numbers. Um, 2 bytes or 16 bits. 16 bits. We're gonna need four hexadecimal numbers. So like 3FA2. There's a hexadecimal number, a 16-bit hexadecimal number, 4, 8, 12, 16. And obviously 24 bits. By the way, 16 bits is 2 bytes long. 24 bits is 3 bytes long. And so therefore we're gonna need one more byte. We're gonna need 2 more bits. So a 24-bit number is gonna be 6 hexadecimals. 1, F, 3, 7, B, C. 1, 2, 3, 4, 5, 6. So that would be a 24-bit number in hex. And then one more is 32 bits. So this is 4 bytes long. It's interesting. It's good to know about bytes because a lot of the communications protocols use bytes. And so this is 6, it'd be 7, 8. So 2 more. 1, 2, 3, 4, 5, 6, 7, 8. How about that? 1, 2, 3, 4 bytes. So that would be a hexadecimal number, even though I didn't use any letters. It just happened to not do that. So this is 1 byte, 2 bytes, 3 bytes, 4 bytes. So that's the difference between hex bytes, bits, hex numbers. We have to be very easy. You really, really need to learn this. And practice is all it takes. It's just a lot more practice.